Hi everybody, today I'm going to be going over the second midterm from Physics 5B in spring of 2024. There are some problems on this midterm related to oscillations, standing waves, and interference. Let's go ahead and dive right in. So the first problem is a oscillation problem. We have a mass on a spring, and we're given this graph of this position versus time graph for the mass. And the problem is asking us for the period of the motion, the speed of the mass, and the phase constant of the motion. So we just want to interpret those things or calculate those things from the graph. All right. Now we're asked for the period. We could try to calculate it from the graph, but it doesn't look that easy to do because we don't have, remember, if we want to calculate the period, we would have to find the time between the peaks on the graph. And maybe we could do that, but I'll just tell you, when I was writing this problem, I intentionally tried to set it up so that it was hard to get the period from the graph. Okay. So my intent here is for you to say, okay, we have the mass and we have the spring constant. So the mass is 400 grams. And K is 23 newtons per meter. And that's all we need to calculate the period, right? From these, we can get the angular frequency, and we know how to get the period from the angular frequency, right? So our period is going to be 2 pi times square root of m over k. And that's just plug and chug, right? We have the mass, we have k, we can just plug in. Okay, so I get this number, 0.83 seconds. All right. Then it's asking us for the initial speed of the motion, the initial speed of the mass. Now we have the initial position, right? That's given from the graph as 7.07 centimeters. And we also have the amplitude, right? We're given the amplitude is 10 centimeters. So the way I would think about this is, anytime you have a problem that's asking you for speed, especially of a mass in simple harmonic motion, that should be a clue right away that you're probably going to want to use conservation of energy, because that's one thing that conservation of energy is really good at, is giving us the speed of things. Now, if we write out our conservation of energy equation, it says our total energy is 1/2 mv squared, right? And I want the initial speed here, v naught, plus 1/2 k x naught squared. So I have x naught, and I have k, and I have m. So if I have the total energy, then I can find the initial speed. And indeed, I do have the total energy because I know the amplitude, right? Because I know the amplitude is equal to 1/2 k a squared. So I have everything I need here to use energy conservation to solve for the speed. Right? I just want to take this equation and rearrange it. So I'm going to get m, just to multiply the whole thing by 2. Okay, subtract x naught over to the other side, and then v naught is just going to be k over m times a squared minus x naught squared, all square rooted. Okay, and this we can just plug into. Okay, so I get an initial speed of about 0.54 meters per second. Right. So again, anytime you ask for the speed, pretty good bet you're going to want to use energy conservation. And again, we know we can do that because we have the amplitude, which gives us the total energy, and then we have the initial position, which gives us the potential energy, and then we can just go through this process. All right, finally, part C is asking us what's the phase constant of the motion. Okay, everyone's favorite thing, calculating phase constants. So again, we have the initial position, and you should always keep in mind, what the phase constant is telling us is it's telling us the initial conditions. And if we know what the mass is doing initially, so in particular, if we know the initial position and we know the initial direction of motion, then we can find the phase constant. So I know x of t is equal to a cosine omega t plus phi naught. And x naught, that's my position at time 0. I just plug in 0 here for t, and I just get a cosine of phi naught. Right, and this equation I can solve for phi naught. So I have cosine of phi naught is equal to x naught over a, which means phi naught is inverse cosine of x naught over a. Okay, so let me go ahead and try to plug in to the inverse cosine. So it's 7.07 centimeters divided by 10 centimeters. I'm taking a ratio here, so I don't need to worry about the units. And this gives me 0.786 radians. Okay, so that's one option. Now, remember, anytime I take an inverse cosine or any inverse trig function, there's two possible outputs. So that's why I've put the brackets here for listing both of the outputs. So one of them is this 0.786 radians, right? And let's draw our phase diagram to check whether this is the one we actually want. And I find it helps to convert this angle to degrees. So just take this angle and multiply by 180 divided by pi. So that's 45 degrees. All right, so that's here. Now, when we take the inverse cosine, the two options we have, right, this is our x-axis. So the two options we have are going to be at the same position along the x-axis. Right, here's our x naught. Right, here's our amplitude. And the 2 points we can have are either here at about 45 degrees or down here at minus 45 degrees. Okay. They're always going to be, when we take the inverse cosine, they're always going to be opposite angles. So if one is positive 45, the other one will be negative 45, right? Or in radians, minus 0.786 radians. Okay, so if we draw in the velocity here, now remember, our point in circular motion, our point in our phase diagram is always moving counterclockwise around the circle. So our velocity is going to go like this. So for this point here, at the angle of 45 degrees, it's moving left initially. Right, because our velocity arrow is pointing to the left. This one down here is moving right initially, because the initial velocity arrow is pointing to the right. Now, which one do we want? Well, to choose, we have to go and look at the slope of our position versus time graph. Okay, and we can see that initially our graph has a negative slope. So that means that at t equals 0, our mass is moving left. All right, so what that tells us is that this point here at 45 degrees, or 0.786 radians, that is the initial position that we want, or the initial phase that we want. So that is our phase constant. Now we have the other option of minus 0.786 radians. That's not the one we want, because that one corresponds to a mass that's initially at 7.07 centimeters moving to the right. All right. And that's it for that problem. Okay, moving on. So we have a problem involving a clarinet. Anytime you see a problem like this where you have some sort of instrument, some sort of pipe like this, then you should be thinking we're going to have a standing wave problem. That's what we have. And the problem tells us we can model the clarinet as an open closed pipe with a length of 58.3 centimeters. So it's open closed. L is 58.3 centimeters. And we're given the speed of sound is 343 meters per second. Okay. And then A is asking us for the fundamental frequency of the clarinet. Since it's an open closed pipe, we know that the formula for the harmonics is NV over 4L. And if I want the fundamental, that just means I want n equals 1. Right, remember n here can be any odd number, and n equals 1, that's our fundamental frequency. Okay, we can just plug in for that. Pretty straightforward. So I get 147 hertz. Not too bad. Okay, part B. So it says, by opening tone holes in the clarinet, we effectively move the open end of the pipe closer to the closed end, decreasing the length of the pipe. So we're changing L now, and we're saying for a clarinet to play a note with this certain frequency in its fundamental mode, how far should the open end of the pipe be from the closed end? So essentially it's asking us if we want this frequency to be the new fundamental frequency, what should be the length of the pipe, right? How far should the open end of the pipe be from the closed end? That just means what's the new length of the pipe. So we want our F1 to be 262 hertz. The formula doesn't change, and the speed doesn't change. Let me give this a prime. The speed doesn't change, hertz. So all we're changing is L, and we're just solving this equation for L. So V over 2 over 4 F1 prime. Just plug it in. Okay, so now I get 32.7 centimeters. Okay, still not too bad. Finally, part C says we can open a different set of holes called register holes, which will cause the clarinet to play higher harmonics of the pipe. So not the fundamental anymore, but n equals 3 or n equals 5. What's the frequency of the lowest harmonic above the fundamental when the clarinet is played with its full length of 58.3 centimeters? So the lowest harmonic above the fundamental for an open-closed pipe is n equals 3, because we only have odd harmonics for an open-closed pipe. So we're just asking if we use the original length of 58.3 centimeters, then what is our F3? And that's going to be 3V over 4L. And again, we're just plugging in. So this is really the only tricky part of the problem, is identifying that we only have these odd harmonics, and that what it's asking for is for us to calculate F3. Okay, so I get about 441 hertz. Which is close to an A note, which would be 440. Okay, that's it for that problem. All right, finally, we have an interference problem. This is probably the trickiest one on this exam. So we have two speakers placed a certain distance apart. They emit waves in phase with each other, and we place a microphone in front of the speakers. It doesn't tell us where we're placing the microphone, but that turns out not to actually matter. We place the microphone somewhere in front of the speakers, and both speakers are emitting waves with frequency of, so an initial frequency of 264 hertz, and they have the same amplitude. Okay. So we would expect these speakers to interfere with each other. Part A is asking us, at this frequency, at the initial frequency, does the microphone detect maximum intensity or minimum intensity? So it's basically asking, do we get constructive or destructive interference? Right? Maximum intensity would be constructive. Minimum intensity would be destructive. So to do that, to determine whether we're going to have maximum or minimum intensity, we could, so there's two ways to think about this. One, we could calculate delta phi, and remember delta phi is going to be equal to an even multiple of pi for constructive interference, or it'll be an odd multiple of pi for destructive interference. Okay, so we could do that. But there's an even simpler way to do it. We know the sound waves are, we know the speakers are in phase with each other. And so whenever we have a problem like this where we have sources that are in phase, the condition for constructive and destructive interference is just a condition about the wavelength. Or, sorry, I should say it's a condition about how the path length difference is related to the wavelength. Okay. So again, this is only for the case where we have our sources in phase. But if the sources are in phase with each other, then if our path length difference is an integer multiple of lambda, m times lambda, we get constructive interference. If it's a half integer multiple of lambda, we get destructive interference. Okay, well, let's just start by calculating what lambda is, because we're going to need that either way. Okay, and this we get because we know V is lambda times F. Okay, so I don't think I put the speed of sound here, but I think I must have given it on the formula sheet. Let's just use the value that was given in this previous problem of 343. Okay, clean that up. And our frequency, 264 hertz. Okay, so just divide 343 over 264, I get 1.299 or 1.3 meters. Okay, now what's our path length difference here? The path length difference is the difference in the distances that the waves need to travel from the two sources to our detector, to our microphone. Okay. So that's just going to be the difference in the distance from the further speaker and the closer speaker, which is just the 1.3 meters that we're given. Right. This 1.3 meters is our delta x. All right. So from the diagram, delta x is 1.3 meters, and 1.3 meters is an integer multiple of 1.3 meters with, multiple of 1. So this is saying that our path length difference is equal to the wavelength, and that's going to mean we get constructive interference. Right, so the problem was asking us, do we have a maximum in the intensity or minimum in the intensity in this scenario? And it's constructive interference, so that's going to be a maximum. Okay. All right, part B says, now we're going to change the frequency. So the frequency is down to steadily increased from 264 hertz all the way up to 1000 hertz. Okay, so this is where we start. This is where we end. As the frequency is increased, how many times does the microphone detect zero sound intensity? So that's asking us how many frequencies are there in between 264 and 1000 where we get destructive interference, right? Zero sound intensity means destructive interference. Okay. So we just want to find, right? We can boil this question down to find and then count all frequencies between 264 and 1000 such that we have destructive interference. Okay. So we want to set up our condition for destructive interference. And again, we can do that in terms of the wavelength. So our wavelength is going to be V over F. And our condition for destructive interference is that we have an half integer, our path length difference is a half integer multiple of the wavelength. So we can rearrange this. So delta x is given, right? We're not changing that. That stays 1.3 meters. And the speed of sound is given. That stays 343 meters per second. So we get an equation for all the frequencies that give us destructive interference. F is going to be equal to m plus a half times v over delta x. Okay. All right. So there's multiple ways we could approach a problem like this. I think the most straightforward thing to do is basically to just plug in different values of m and check whether they fall within the range. Okay, so we're going to start with m is equal to 0. Now, I think the easiest way to do this is to calculate the numerical value of v over x. So this is, let me move this. Okay, so v over delta x, that's 343 over 1.3. So I get 264. So for each m that we plug in, we're going to get a different value of the frequency. Right, starting with, so if m is equal to 0, we just get 1/2 times our frequency. That's 132 hertz. That's outside of our range. For m equals 1, we get 3/2, right? 1 plus 1/2 times 264 hertz. Okay, so what is that? So that's just going to be 3 times 132. So what is that? It's 396 hertz. Okay, so that is within our range. M equals 2. 5/2. So 660. And we keep going until we move out of the range, which went up to 1,000 at the maximum. Okay, 924, and that's going to be it, right? So these are going up by 264 each time. So once we get to 924, we know we're done. The next one is going to be higher. So we find these frequencies that are in the range from 264 hertz to 1000 hertz, where we have destructive interference. So our answer is 3 times. Okay. Finally, part C. So same question now. We're increasing the frequency from 264 to 1000. How many times do we get maximum sound intensity? So same exact setup. The only difference is now, instead of our condition for destructive interference, where we had delta x was a half integer multiple of the wavelength, we want constructive interference. So we want this to be a whole multiple of the wavelength. So we're going to have m times 264 hertz. Okay. Sorry, I skipped a few steps there. F is going to be mv over delta x, which is m times 264 hertz. Okay. So do the same thing. 0 doesn't work. That's frequency is 0, which is nothing. So m equals 1. That's 264 hertz. Okay, we could include this one or not. That's the frequency we start at. I was really thinking about when I wrote this problem of the ones in between 264 and 1000, but if you included this one, that would be fine, because it was a little ambiguous. Okay, then we have 2 times 264 hertz, which is that 528. Okay, that's definitely in our range. M equals 3 is, just do it, the calculator, 792. Okay, and that's, we can stop there, right? Because the next one is going to be for m equals 4. We get 1056, which is too high. So now we just get these two frequencies. So the answer would be 2 times, or if we include the initial one, which would also be fine, then we'd get 3 times. Okay. So that's all for that. Thank you, everybody. Let me know if you have any questions or any feedback on this video, and take care, and I'll see you later.